Well, that's us recording.
Okay. Right. Hello, everyone. Guess it's time to start. Can you hear me in the back? Yeah. Can you hear Connor in the back?
Can you hear me in the back?
Yeah. So as you can see, Connor is two-dimensional today. It's his turn, but he'll be with us anyway. Any announcements before we start, Connor?
Yeah, I've taken my pronoun pills and put my helmet on. Uh,
Sorry.
yes, yeah. Well, homework's good to go. As of about half an hour ago. Um, and yeah, I'll be back in three dimensions uh next week, I hope. Um, but no, we're just rolling along. Um, so um, I guess we'll get going. Um, so if you can see my screen, I can't really see what you can see.
Yes, we can see your screen. Yeah.
I can see a decapitated Fred. So- right. Um, okay, so here I've got our good old type of Spuds and Lemons numbers. And I've got our relation that says when one number is less than or equal to, so less than or equal, another number, where I explain how the relation, or what the relation is, by saying what rules are available for proving it. So I say there's a rule called les that proves that zero is less than or equal to anything, and a rule called less that says if you're trying to prove that the relation holds for two big numbers, um, peel the spuds off one each and keep going. So I suppose I'll just do an example, prove that uh, 2 is less than or equal to 3. Right. So we've got two spuds, so I'd better choose less. We've still got two spuds, and now we've got a 0 on the left. So there we are. So that's the deal with these relations is that you specify them by saying uh, exactly the only ways that you have available to prove them. Okay, so one of the things we're going to look at today is the idea that um, uh, anytime you have a uh, a monoid, that gives you a particular way to construct uh, a relation, and that relation will always have a special property. So here's adding defined as an infix operator. So just a little thing to say about infix operators. They're made out of symbols like plus and times and minus and less than and greater than. Um, they take two inputs, and when you want to give them both inputs, you put them between the inputs. When you want to talk about them as a thing in their own right, so when I want to say plus is a function that takes two numbers in and gives a number back, the thing itself gets talked about by putting it in parentheses. So uh, plus in a pair of parentheses has the same status as the word plus that we used last semester. But it's just nice that we could write things that are a little bit more readable, but we've got a bit more overhead to see what's going on. Anyway, I'm going to define a relation that says you can how to get from one number to another by adding. So that's prop add on number. So it's a relation between two numbers. And there's one way to prove it. You prove add on AC by adding B, where you to prove that you can get from A to C by adding B, you have to prove that A plus B equals C. So that's the definition. The A and C are related if you can figure out a B that you can add to A to get C. And I'm very much hoping that this is going to turn out to be the same idea as this thing, just cooked a little bit differently. Okay. So let's prove that this is a preorder. What's a preorder? R is a preorder. It's not like telling the restaurant today what you're going to order from them tomorrow. It's if you can prove RBB. So everything's related to itself, and also things you can play join the dots. If you can get from A to B, you can get from B to C, then you can get from A to C. Exactly what was not true about stone, paper, scissors. Right, so let's get on with it. Prove add on BB for sake of argument. Right. Well, how should we prove it? Can you think of something we can add to B to get B? Any
Anyone? There's this hand symbol, which looks a lot like nothing in the room.
okie dokie. So that's going to be bar.
Oh, that's not good. Oh, you're back, Connor.
Something strange has happened.
Yeah, I think we lost some internet connectivity, but all fine now.
Right. So I also had an Emacs wobble. Right. Uh, so here we go. Funnily enough, the thing we have to make sure of is that B plus 0 is B. And as you can see, I haven't actually dropped in the proofs that addition behaves like a monoid with neutral element 0. So let me just, I think I left them conveniently on the lecture page. So I'm just nipping across to a thing that's not on the screen. Let me just grab a load of library stuff. Well, no, just a little bit at a time, actually. And if I paste that in, then I ought to be able to just do that. So I dropped in the bit of monoid law that we needed, and now this thing is fine.
We, we, we kind of missed a crucial moment, so maybe we explain this one again.
Okay, so
Explanation lost to the internet.
right. So let me comment out this perfectly standard monoid law. So we're being asked to prove add on BB. We decided we were going to do that by adding 0, and it asked us to prove one of the monoid laws. So what do I do? I make sure that the monoid law that we need is sitting there in the background, and then I can even say that's given, and Emacs has done something really weird with, so I've made to go away. Or I could say given, or I can even just delete it. So that's step one. Are we cool with this so far?
Yep, I believe we are.
Right. Then let's I guess I should do an example, of course. Can we prove add on? What did we do earlier? Same thing here. How are we going to prove this? Any takers? What should we? Well, there's only one game in town. We have to say what to add to 2 to get 3. I think we'll find 1 is what we need, and ask is perfectly happy just to do the arithmetic for us and check that that's true.
Kind of what happens if you choose the wrong witness.
Okay, let's see. So I'm just gonna park that there. So if I say by adding 2, then it asks me to prove false, because it figures out that 2 plus 2 is 4, and then it tries to prove that 4 is 3, and it knows that 4 is 3 if 3 is 2, and that 3 is 2 if 2 is 1, and that 2 is 1 if 1 is 0, and a spud's not a lemon, so that's bullshit. So let's when we get into the territory where there's some actual arithmetic to do, it does quite a lot of work for us. So let's put 1 back in the right place and have a nice prover again. Okay, what's next? We want to prove that if we add on A, B, and we add on B, C, then we get add on A, C. Okay. So we've played variants on this game before. The technique is that you introduce the assumptions one at a time, and you squeeze as much information out of them as possible as you go along. So we'll do 1 step of implication introduction. That's the only game in town. And now we're given an assumption. And instead of doing more implication introduction, let's get the value from the assumption we've just introduced. So we say from add on A, and then it makes up a stupid name for the thing. There's some X that got added to A to make B. Well, that's good news because there's a B in my goal, and I can get that substituted out if I say from B equals A plus X. So I choose an equation which has a variable on the left and something that I know it's equal to because of this assumption. Ask knows that equality is symmetric. So it'll look for a proof that B equals A plus X and it will find one. And then given that, it will be happy to replace B by A plus X. So there we are. We're now proving that we can add on something. We know that we can get from A plus X to C, and we have to show that we can get from A to C. Well, now I'll do implication introduction again. And I need, given this thing, to prove this thing. Well, I'm not quite ready to prove this directly yet because I don't know how to get all the way from A to C. But I know that I can get from A plus X to C somehow. So if I do a from on this assumption, ask will again choose silly name, but there must have been some y that we can add to A plus X to get to C. Okay. So can we figure out what to add to A to get C?
Everyone see it? X plus Y, yeah, that
Sounds good to me.
excellent plan to me.
By adding X plus Y. And now we have to prove that, well, actually, what I should have done before that is oh, what happened there?
Too many C.
Too many C's, yes. Right, that looks good. And I'll put the brackets in so that we know what we're doing. And now I say by adding X plus Y out. That's that way. But hey, that's another one of the monoid laws. It's almost as if we were doing this deliberately. So why don't I go and fish that out of somewhere else I've got stashed. So if I park that, oop, what's going on? There's some strange interaction between Emacs and Zoom that means things are not quite doing what I expect them to do. So, oop, and also my fingers are doing bad things with the font. So hopefully that's given. Or even invisible. Okay, so we've managed to show that add-on is a preorder. That you could get from anywhere to itself, and if you can get from A to B and B to C, you can get directly from A to C. And it turned out that what we needed to establish those things was exactly that uh, plus is that plus satisfies monoid laws. Okay.
Notice we didn't use any of the definition of plus itself, right? We just used the fact that it had a unit, which is 0, and that it was associative. But we didn't care about the exact equations that plus satisfied. Okay.
Right. So should I throw this in Mattermost and then
Yeah.
invite you to prove that these two notions are equivalent? So I guess I'll do it front of house. There you go. By the magic of the internet, that should be coming your way.
Yeah.
And I guess I better stop sharing. Um, so that you can start sharing.
Indeed. Okay. So that seems to be working, right? And I think, Connor, what you want me to do now is to think a little bit about add-on versus less than. Is that right?
Yeah.
Yeah. So at the very beginning here, Connor reminded us of how we define the less than relation, right? And then we define this new relation, add-on, but it's maybe worth thinking about how these are related, if they are, right? So when is it the case that we can add on something to a number A to get a number C? Well, intuitively, this should be the case exactly when A is less than or equal to C, right? Because if A is smaller, then we can take the difference and add that on to get the bigger thing. So if we have that A is less than or equal to C, then we should get an add-on AC, but also the other way around. If we know add-on AC, that means that there is some B such that A plus B equals C. Well, that should mean that A is actually less than or equal to C, right? Again, because we have this difference that witnesses this. So we could hope to prove that, which one is the easy one, Connor?
Oh, well, you should prove that they're equal,
Yeah.
but then they'll split out into separate goals.
Right. Yeah. I always like to start with the easy direction, but okay, so I'll start with a random direction. So I would like to prove this. And I would like to prove it the other way around, right? And as Connor is saying, I could just prove that they are equal as propositions by equivalence. And then I have to prove both directions, right? So I guess I could just do it like this.
Yeah, except that you will need to do separate. If you're going to prove these inductively, you will need to do them separately.
Right. Yeah. So that's a good reason to not do it like this.
You can that's the tidy packaging that you can put at the end.
Yeah. Comment it out for now.
Yes.
Okay. So this is what I would like to do. I would like to show that if I know that A is less than or equal to B, then I get an add-on AB. And conversely, if I know an add-on AB, then I get the proof that A is less than or equal to B, right? So these are the same. Okay, so how do I do this?
I would just recommend for that you rename B to C. Just because, and don't forget to do it in the, yeah, there.
Fair enough.
Yeah, just because of the way we've defined it. B is the difference.
Yeah. And it's, I mean, it's a minor thing, but it can be very confusing if you use different names in the definition here and when you use it, especially if it's the same names, right? Okay, so step one is a free step because I'm trying to prove an introduction. So, well,
No, it's not.
it's not. It
Ask
could
is
be a
crap. So you need to do inductively first.
Yeah, but if I want to do inductively, then I want this whole statement inductively, right?
Yeah.
I want to assume the assumption and then try to prove this inductively. That won't work. So I'm going to start with inductively, and then I have to think what I want to do induction on. I have two choices, A and C. And I suppose because the less than relation is looking at the first component, so then maybe I'll pick the first one.
But it doesn't really matter.
Doesn't really matter because everything will go down eventually, right? But okay. And now I can do them by imp I, right? Okay. So now I have to start thinking, right? But I don't have to think too much because I have two possible moves available to me, right? I can say, okay, I know what the answer is. I'm going to say by adding. That's how I introduce this thing. Problem is I don't know what the answer is yet, right? Because I don't know how much to add to A to get to C. So the only really sensible move I can make is to interrogate what I've been given, right? So I've been given that A is less than or equal to C. Well, I could say, in what way is that possible? And then there's two cases. So either A was said or A was a successor. A prime. C was a successor. C prime. And we know that A prime is less than or equal to C prime, right? So notice that in this case, my goal has changed a little bit. Now I have this extra, since this is my A, but I know now that A is S of A prime and so on, right? Okay, let's deal with the base case first. So here we know that A is 0, and we are asked to find something such that if we add that something to 0, we get C. Right? Can we think of anything like this?
Add C.
Add C, indeed. Yeah, because 0 plus C is C. That sounds promising. So I'm going to say by adding C. And thankfully, we don't have to prove anything because the proof obligation we have is that 0 plus C equals C, right? But that was one of the defining equations for plus. So Ask is just happy to give us this one. Okay, so that's good. It dealt with the base case. What about this case? Well, so here we have now exposed that two smaller things are in this relation, right? So because we're doing it inductively on A, and A prime is smaller than A, we are entitled to an inductive hypothesis here. So I think I'm going to ask for that. So I copy all of this. This on the new line. And then I make sure to change these to the smaller things that I care about. Okay, try that. So ask has given us the conclusion of this because it knows this is true here. And it's happy to give us this conclusion because we have done an inductively on A, right? So now we know that there is something we can add to A prime to get C prime. So how can we use that to show that there's something we can add to the successor of A prime to get the successor of C prime? Well, here, we've just put the successor on both sides of this equation, right? So we should actually be able to use the same something from here to show that the same thing here, because things should balance out. There's one more here and there's one more here, right? So I'm going to interrogate how it's possible that this is true. I'm going to say from this. And then I said, well, that's because A prime plus K, or maybe I can even call this B here, is equal to C prime. Okay, so now I could do by adding B and try to muddle through, but I think the good move is the move that Connor showed us, which is to first replace the C prime here by the more informative thing here, right? So I'm going to say from C prime equals A prime plus B. So what this is doing is it's replacing the C prime with A prime plus B, right? Okay, so now I'm kind of in a good position to say by adding B. Okay, let's see what happens. And thankfully, that equation now is just true, and we don't have to fiddle around with moving successors here and there. Ask is doing that for us, right? So
Yeah, that's
yep.
good. I think adding B would have worked, but you're still right to just go on autopilot and say, I could rewrite C prime.
Right,
You know,
yes. You're saying I could have done this directly here.
I think you could. Let's find out.
Right, let's find out. And there's a raised hand.
Hello, I just wanted to ask, does the add-on function, I kind of missed it, but does the add-on function add to the first successor? Let's say like prove add-on successor A dash. So something added on to successor A dash equals successor C dash.
Yeah.
Yeah, let's go. Right, so first of all, I'm afraid, Connor, that did not work. So let's go back to this version.
I'm slightly surprised it didn't work, but anyway.
Unless I made a mistake, but this works in any case, right? And now should we go up and look at the add-on predicate?
Yeah.
So plus is defined in a certain way, right? But then after plus is defined, we define what it means for add-on AC to be true. And we say, well, add-on AC is true if you can provide a B such that A plus B on the right is equal to C. And it happens to be the case that A plus B is the same as B plus A, but here we have defined it to be on the right. So you have to explicitly appeal to that symmetric proof if you want to use B plus A instead. Does that answer the question?
Yeah, that answers the question quite well. Thank you very much.
Okay. Right. Okay, so we did this. I think maybe now it did work, Connor, and I was confused.
Yeah, I'd be surprised if it didn't.
I think I saw this next goal and I thought that was a leftover goal of this one. Yeah, so it just works. Yeah.
Yeah. Because it wants to prove successor of A prime plus B is successor of C prime, and it knows it can peel the spuds off. You know, it's automatically saying, well, successor is successor, that's a free hit. And then it finds A prime plus B equals C prime as a given.
Yeah. Okay, nice.
But yeah, I agree that um, the instinct that goes, if you see an equation that lets you eliminate a variable, just do it. Fewer variables is less of a headache.
And it's never a bad move. You can't get into trouble that way that you weren't already in. Okay, should we try the other direction?
Let's do it.
So this time we want to show that if we have add-on AC, then we know that A is in fact less than or equal to C, right? And I think we're going to start in a very similar way. We are not going to be able to do this in one go. We need to do some induction. So I'm going to start by saying inductively A. And then I'm going to do an introduction. And then I'm in the same kind of situation as before, right? Where I a priori have two moves available. I could prove this directly, or I can interrogate my assumption, right? And again, I can't really prove this directly because I don't know what A and C are, right? Okay, so, well, I also have one more thing I can do. I can actually look at A and C, right? Which might be a good idea here. So should I do this? So I remember that the less than relation is kind of first looking at the first argument, right? So I will do the same thing. So I'm saying from A is either 0 or the successor of some A prime. Okay, if it's 0, then I'm happy because I know that 0 is less than or equal to C by this. If it's not 0, then in order to be happy, I better look at what C is, right? And if C is 0, then I'm unhappy. This looks bad. But if C is a successor, then I have some hope, because then here I can say by this constructor, I have to prove this. And I can get this by the induction hypothesis. If only I can prove this. But I have some hope of doing this because I know add-on C. Right? But maybe I should have not done all of this and unpack this as soon as possible. I think that would have been a better move. So unless Connor stops me, I'm going to just go back and do that. So this is what usually happens, right? You follow your nose and then you realize your nose is not as good as you think it is. But then you can always go back and change things, right? So keep this in a comment just in case for now. Except I deleted too much. And then I'm going to say,
I'm obviously cheating by looking at what we did yesterday.
so I do a from on this just to expose that information, because now I know that there is a B such that A plus B is C. And then I'll follow this instinct to eliminate the variable C. So I'm going to say from C equals A plus B. And then here, I now have something that looks a little bit better. Wait. Okay, so now obviously I have to look at something. Maybe not A anymore, but plus is defined by looking at, yeah, actually not A. Plus is defined by looking at the first argument, right? So if I want to know what this is, I better look at the first argument too. So I'm going to say from A. And then I have these two cases again. Okay, and one case is easy. And in this case, now I'm in a slightly better shape, right? Because I have a successor here and I have a successor here. So I should be able to say by this. And then here, I now have something smaller. So if I use the induction hypothesis, B is this. Okay, then it's enough to show this add-on, but that's an easy add-on to show, right? What do I have to add to A prime to get A prime plus B? Well, that's B, right? So that finishes it. I think you could have kind of muddled through this way as well, but clearly this was more complicated, right?
Yeah. It's the usual thing where uh, uh, you could have got your hands on some equations by unpacking, and that would have simplified the goal. And then you ended up with it being with just getting your hands on the equation slightly too late. The other thing that you could have done, which would be a perfectly sensible way to proceed, is to pull less than or equals A plus B out as a separate inductive proof.
Yeah. This,
So that thing.
okay.
Yeah.
This looks like a sensible statement on its own, right?
Yeah.
Okay, and now if I wanted to package this up as an equivalence, then I guess all I do is I say from the two proofs we just did.
Yep.
Change these to C's as well.
Yep.
Okay. Connor, do you have anything else to add to this?
So this, no. And I'm wondering if that's half time.
Yeah, I think so, right? So we take a 10-minute break and we continue again at 10 o'clock.
Yep.
Yep.
I wonder if there's actually a way I can hit pause on the recording, which might save some editing. Uh, okay, let me just see what I've got kicking around. Yeah, I guess I could start a share. Okay, so what I want to do next is think a little bit about this add-on business. If I've got two numbers, X and Y, what's the biggest number that I can still get to X and Y, to both of X and Y from by adding on? So I want to show whatever it is. So I want an operation. I'm not sure what to call it, but we can rename it in a moment. Takes two numbers. Right, what I want to prove is that you can get from big from xy to x, and you can get from big from xy to y. Right, now that much is easy because I could always choose big from xy to be 0. So what I want to show is that if you can get from somewhere to x, and you can get from the same place to y, then you can get from A to big from xy. So now we can't just pick 0, right? Because you can get from 2 to 5, and you can get from 3 to 5. Or what am I saying? Yeah. So yeah, if we choose, if X and Y are 3 and 4, and we say that big from of those things is 0, of 3 and 4 is 0, then I can just say, well, A is 2. I can get from 2 to 3. I can get from 2 to 4, but I can't get from 2 to 0. So what do we have to pick? How do we so what's the number that's only just small enough to get under both X and Y? I think this has we've seen this operation before as a more standard name.
Anyone? Was there something up there in the back? It's worth a guess. Sorry, one more time. Inductively X. Yeah,
Yeah.
so we have to define it inductively, that's true, right?
Yeah.
But Connor is looking for a more common name than big from for this operation.
It's It's one we've seen before.
Let me try and just say again what Connor said in case that jogs any memories. So these first two prove here, big from xy add on x and big from xy add on y, right? They say that this thing should be smaller than x and y, basically. And then what Connor was saying that, well, it's easy to do that, pick 0, right? So that's boring. So then this next thing here says that this should be the largest thing that's smaller than x and y, right? If you have anything else, an a which is smaller than x and y, then a is actually smaller than this big from operation, right? So these two things kind of pushes big from to be small, and this is pushing it to be large again, so it's not too boring, right?
Yeah. So if x and y are 3 and 5, what are we going to pick?
What's the largest number which is smaller than 3 and 5? It's 3, right? Yeah.
Yeah. So we just have to pick whichever of the two numbers is the smaller.
Also known as the minimum function, right? You're missing some ons in your add-ons, by the way, Connor.
Oh, yes. I'll sort that out once I've done this. All right. So yeah, sure. All right. So if one of our numbers is 0, the minimum is 0. Otherwise, we better look at the other number. And if our second input is 0, the minimum is 0. Otherwise, both our numbers are at least 1, so the minimum is at least 1. And then we can figure out what the rest is by recursively computing the minimum. And we have a choice of ways to prove these things. And I'm trying to decide on the face of it what's the nice way of doing it. And maybe it's to just go via less than. So let's do that. So I can say from less than min x, y, x implies so that's one way to do it. And then this is better going to be inductively x. Okay. Bit of tidying up of the names. Okay, so here we want to do test because we're going to get some computation. And can we prove that z is less than or equal to itself? We sure can. Okay. What happens next is, again, we've got this thing here. We don't quite know what it is yet. It's currently stuck. Let's get it unstuck. And I'll just fix up names. Okay. Now here I'm going to say test. and now the minimum was 0, and the other number was something else. So I can say by, again, that 0 is less than or equal to anything. And then here I say test, and I get myself some computation, and I say, well, I've got 2 spuds, so I can peel them on in each position, so I can peel them off, and what I get left with is exactly the induction hypothesis, with all the x's and y's replaced by primes when I take the s off. So that's hopefully I can now say given there. Right. Now, I wonder what to do for this one. But actually, I know what to do for this one. I'm just going to nip over to my stash of handy facts about plus. Grab some things. So, more stuff we know about plus. We know that plus is commutative. Right. So yeah, there are lots of ways to do this proof. We could have done it, and indeed, last night when Fred and I were rehearsing, we just did this directly by induction on X. So I'm just cooking it differently to muck around. So now let's figure out what's gonna happen here. Did I actually want that? Maybe I did, maybe I didn't. Actually, yeah. I'm not sure I did want that that plus is commutative. Might want that min is commutative,
Indeed.
because if I can just swap these two over, then I'm there. So maybe I'll prove that min is commutative. Right, so I want to prove min xy equals min yx. And then what am I going to do? I'm going to prove that if A equals B, and I know add on AY, then I know add on BY. So let's just get ourselves in the right position. So this replace equal for equal. So now if I replace B in the goal by A, it reduces to the thing we had earlier. And now I'm going to say from min yx equals min xy, and add on. Actually, maybe the thing I should do is to change variables just to make it absolutely clear what's going on. I'm going to exchange the roles of x and y here. Okay. So I'm going to make use of this fact instantiated with the commutativity of min. Okay, and now I have to prove those two. And we get no sub-goals, but because we haven't proven this thing yet, it's still not gone green. So let's just do it. Bit of a bash. And then this is x prime. Oop. X prime. X prime. What do we do? Well, we're going to have to look at y, aren't we? And we get no case for 0. That just computes away. Right. Okay, and in this step case, I'm in exactly the situation where my zoom window is stopping me seeing what I'm doing. We say test, and that's actually enough to reduce it to the induction hypothesis. The successors bubble to the outside where they get stripped away, leaving us exactly with the same goal, but for the primed things. And now our proofs have turned to proven in this thing. I'm a guess as to what the answer to the question is, but well, do you want to do the other one?
Why don't you do it if you're set up for it?
Yeah, I mean, I guess um, what I'm actually going to do is to do it the less than way.
Mm-hmm.
So I'm going to prove that if I know a is less than x and I know a is less than y, then I know that a is less than min xy, because less than steps nicely with the way min computes. So let's, again, just make sure that's going to get us there. So by imp I, and now I say from add-on ax implies leax. I'll just take that to a new line. And now I've been given a handy fact. And I play the same game again with the other assumption. And it gives me the other version. And now I say that I want to make use of the fact that I want to go in the other direction. And now I have to prove that. But any minute now, I will know this much. And it's the usual deal when you've got two hypotheses, you have to use them one at a time. So if we've got two arrows, we need to do two froms, but that much will be fine once we've knocked this off. And now, what am I going to do? Well, in fact, I can do inductively on anything, I expect, but reflexively, I'm going to do induction on X because that's the thing that min is stuck on. But I would be surprised if it didn't work for any of these things. Okay. So I'm going to do by implication introduction. Right, and fine. Okay, and now I've got something I can extract juice from, namely this thing. And because I know that if I ask why this is true, I'll learn something about A. I've still got A's in both of these pieces of my goal, so I'm not going to introduce this assumption until after I've made use of this given. So if I say from A is less than or equal to X, I'll get two cases with terrible names. So fix up names, X228 had better be A prime. X229 had better be X prime. And I'll just take that down there. Okay, so here we're gonna win. We're trying to, ultimately, we've got a boring assumption. Let's move it to get nearer the goal. But now we're being asked to prove that 0 is less than or equal to something or other. So that's just straightforward. Okay. So now what happens? Well, I think I'm going to make use of this fact. Right. So what's going to happen? What does this tell us that's going to help? I mean, we could do from Y and worry about whether or not Y is 0, but we can go more directly. There's only one way this can be true. Right, and now we've got, I've got to do my other Y prime. And now we're in a good position. I can say test just to see what's going on, and we get a bit of computation, and now we've got two spuds. And I have to prove that A prime is less than or equal to the minimum of X prime and Y prime. And that's looking very promising. What I do is I go from, and I grab my original goal, and I prime all the things. And it's happy for me to do that. Again, it's a two-step from. Do that. And then we're done. Because we had all of those pieces. And now we have made it all the way to the end. Okie dokie. So what do I need to throw into the Mattermost? All of this lot.
I mean, that's good anyway, right? We're doing Malta next. We don't take it.
Yeah, okay. Don't need to fling that across, but I will need to put it in the right, I see a hand on the Zoom.
Yeah.
Hi there. I was just wondering for the last two parts that Connor just did. You know, for like that the LE question where he was proving a less and equal to wasn't originally there before, and he had to write that new question just to prove the second question, the add-on question that came on later. Will we have to do that in the exam, like write new questions that we have to prove to be able to prove the questions that are given?
Yes, it sometimes will happen that if you so here I we had already established that uh, uh, that these two are equivalent. Um, so it's not a big stretch when you know two notions are equivalent to ask which would be easier to work with. So it's extremely likely that in any situation where it was important to do that, um, there would be a clue like this, right? Um,
Mhm.
so um, uh, it's the situation where yes, if it's a good move to switch out one equivalent notion for another, um, then uh, some kind of earlier subproblem would flag that up, right? So um, uh, so some creativity may be necessary in that sense, right? Not all moves are forced, um, but uh, but some moves are signposted by clues. You know, if you're if you're asked to prove an equivalence, it's probably going to be important.
Okay.
So yeah, here, I mean, again, in rehearsal yesterday, we did this directly
Directly without the secondary question.
without the secondary problem. Um, and yeah, it was okay. Uh, there's so it's also the case that uh, there are kind of plenty of ways to do lots of these problems. There's not, I mean, especially when there's this much equivalence lying around that
Mhm.
um, that yeah, you could do this directly using factor by plus. Um, and it's even possible to do this in an interesting way um, by directly computing, right, how much bigger is min xy than, or how much bigger is x than min xy? Well, you can compute, you can actually do the subtraction to
Uh-huh.
figure out what has to go, what's the witness for what you can add on in each of these things.
Okay. Awesome. Thank you very
Yeah,
much.
yeah. So lots of ways to solve these problems. Um, it's not that I chose this because it's the only way to do it, but because um, I thought um, that the way less than gives us zeros and successors would be useful to force, in particular, this computation to happen. I knew that going from less than would fit with the way less than gets proven. So that was but yeah, I'm trying to remember what was the proof we had. Maybe I'll not look at it right now. Maybe I'll stop sharing and let Fred talk about multiplication. And then I'll go and look at yesterday's.
So we introduced this add-on using plus, right? But we could also imagine doing this for other operations, not just for plus. And then, so the add-on happened to correspond to the less than or equal relation. If we do it for another relation, we wouldn't expect this to be less than or equal. We would expect it to be something else. But we could still do it, and it's a fun puzzle to think about what it is, right? So I'll take this just for comparison, put that in a comment down here. And let's do the same thing for multiplication. Do we have multiplication? We do not have multiplication. Let's give ourselves multiplication.
Yes, here's one we prepared earlier.
So here's multiplication, infix again, and it's doing induction on the second argument. So we're saying that x times 0 is 0, and x times the successor is x plus, and then we do the smaller multiplication, right? So it's repeated addition on the right. If this is 5, then this is going to be x plus x plus x plus x 5 times, right? Okay, so let's follow this recipe and define a new proposition called malon, which is a proposition relating to numbers. So I'm saying this is the name of it, this is the type, it takes two numbers. And then I have to say, what does it mean to prove this proposition? Well, to prove mal on a C, well, you do this by mulling with a B. So here I'm naming the method. It has this parameter B, and then you still have to fulfill a proof obligation, which is to prove that A times B equals C. So exactly the same pattern as up here, except that I replace plus with a times. Let's see if I accept that. Something went wrong with the definition of times. Why is that?
That's mildly alarming, given that it comes from one we did earlier.
Okay, let's actually look at the error message.
Yeah, that's very peculiar. I mean, what happens if you just blarge on and do it? Right. I don't know what's going on there at all.
Yeah, okay, so now it seems to be working again, right?
Replace it with an exact replica.
Yeah. Very strange. Okay. So here's the definition of malon. And now we could hope to prove, so we can't hope to prove that this is the same as the less than equal relation, right? because this should be very different. It is not, well, we have a good example of this. Maybe not off the top of my head, but we could still hope that this is a pre-order, right? So that so what did this mean? Well, it meant that we can always go from A to A, and that we can go transitively, right? So if I know malon A, avoid.
Yes.
So if I can go from A to C and I can go from C to E, then I can go from A to E, right? If I could only type. So this is like saying we can stay still on the spot. And this says if I can go in one step from A to C and another step from C to E, then I can go in overall from A to E, right? So we can still hope to prove this. So let's see if we can do it. Let's do this one first. And okay. So we don't have that many moves available to us, right? All we know about malon is that we have a canonical way to proving it by mulling. So we have to come up with a B such that A times B equals A. Can anyone think of such a B? Yep. 1 looks good to me because A times 1 should be A, right? So I'm going to say by mulling 1. Okay, and then happily, there is nothing to be proven because ask just computes and sees that A times 1 is just 1. That's like adding A 1 times, right? Which is just A. So that was easy. Let's see if we can do this one. So here we could think, do we need to do this by induction on anything? Well, hopefully not, right? But it doesn't hurt to say inductively A, just in case. And then we have to assume this. And what we learned before was that if we are given one of these facts, which can only be proven one way, and is in fact proven by giving us a little bit more information, then it's usually a good idea to just unpack that as soon as we can, right? Because it will then, propagate that information to our goal, and that's having more information is a good thing when we're trying to prove things. I'm going to do a from mul on AC, and then I get given that there is some B such that A times B is C. And then I'm going to propagate this information to my goal. So I'm going to say from C equals A times B. So now that's replacing this C with A times B. Right. Okay. And then I go again. So I'm trying to prove an implication. So I'm given this thing. And again, just interrogate that immediately. Emacs. Okay, so here I get given that there is some D such that A times B, that's my left-hand side of my malon, times this D is equal to E, right? Okay, but then again, I have an E in my goal, so I might as well substitute along this equation. Except I want to replace E by something, so I'm going to say E equals this. And then, if I put these brackets in properly, then again, I see that I'm kind of in a good place, right? Because I'm asking the question, can I come up with some number such that A times that number is the same as A times B times D? Well, that B times D, right? So I'm going to say by mulling B times D. Okay. And then again, it looks like I'm kind of happy, except that I'm asked to prove associativity of multiplication, right? Because here I had it bracketed one way, but for the mulling constructor, I really needed to be bracketed the other way, right? Thankfully, we have prepared this. It's in because you've done this before. See if it still works. Yes. And now this should just be given. So we see that again, all we needed in order to get a preorder was that this operation was the operation of a monoid, right? So that there was a unit and that it was associative. And we didn't particularly care about what kind of definitions were actually here. So we did use that x times 1 is x, but that's the monoid law, right? And apart from that, we didn't particularly care what x times 17 was, for example. Okay, should I fling that over to you, Connor?
Sounds good to me. See that you're typing? Right, cool. No, I have to hit show more if I want it. Oh, it's got selected. Good. Just, yep. So I'll paste that into my file.
Don't forget to share your screen.
I will share my screen in just a moment. Just wanted to finish the paste. So share Emacs. Okay. What do I want to do now? I want to just point out a few little things about Malon as a preorder. We say that it has a bottom element and a top element. So is there a place where you can get from to anywhere? What's the lowest thing in the Malon order? Right. We could do it with add-on as well, right? It is the case that up here we proved it was a preorder, and it's got a bottom element. Because you can get from 0 to anywhere, right? Right, and now, what's the thing that does that job from Malon? Any takers?
Yeah. One taker.
Let's see. So we're hoping that we can get from 1 to anywhere by mulling X. And we know enough monoid laws that that's true. Okay. Now, we know that um, there is no way to give a biggest thing in the add-on order. There is no top element, right? If we wanted wherever we are, right? If we wanted to prove a, something, we'd have to think of a number that was bigger than all the other numbers. And that's not going to happen. Bigger in the sense of getting bigger by adding, right?
Mhm. Mhm.
Uh, so reachable by adding is our ordinary notion of less than or equal to. But Malon isn't our normal notion of less than or equal to. So I want to see if we can figure out, is there somewhere that we can always get to by multiplication?
We could do mull on x to 1, and that's by mulling by 0.
Well, if we put 1 here, then we're not going to get there by 0. But you're right that the point is that we can always multiply by 0.
Ah.
So we can always get from x to 0 essentially by nuking it, by mulling with 0. Uh, so that's even just direct. So it's nice that in the world of, in the pre-order of multiplying, there's a bottom element, 1, and there's a top element, 0. And then there's a familiar name for all the numbers that aren't quite the bottom element, that are only just above 1 in the multiplication order. Does anyone know what those numbers are called?
Anyone? You're
So
asking for the numbers that can be reached in one step, so to speak, right?
yes, that the only thing below them in the mull-on, they're not 1, but the only thing below them is 1.
Could you say factors?
Well, it's related to factors. It's a particular. Um, so yeah. So let me just write the thing. So what are the numbers x which are not 1, but uh, um, where if mul on ax, then a is 1, or a is x, of course, because you can always get from x to itself.
Mhm.
Yeah. Sorry, one more time. Least common divisor numbers. Not quite, right?
Yeah. So
Prime numbers, yes.
it's the prime number.
Oh, prime numbers. Oh.
So they're the things that that play the role of only just not at the bottom. And indeed, greatest common divisor is the thing that plays the same role for multiplying as min does for the add-on, but greatest common divisor is a really tricky program to write in ASC. So that's a nice little piece. So yeah, the message here is that every monoid gives you a preorder. Right, so what I'm going to do now, because we've not got much time left, is just have a quick introduction to the homework for Tuesday. So let me, instead of sharing that, let me just make sure I've got it sitting in a browser. And share that instead. Share that. Okay, so this I did as I was drinking my first cup of coffee. Is next week's homework. So, first of all, I give you the data type of bits with O and I representing 0 and 1. And then I define the Boolean implication relation. And all I'm doing is I say there are 3 ways to do it, corresponding to the 3 lines in the truth table where 1 comes out, right? So I'm saying that false implies false is one way to prove an implication. False implies true is one way to prove an implication. And true implies true is a way to prove an implication. So the only one that's missing is if true things don't imply false things. Okay, so I'm asking you to show that that's a preorder, but I'm also asking you to show that it's not just any old preorder, it's the preorder induced by a monoid, just as add-on was induced by plus and mull-on was a preorder induced by times. This preorder is induced by some monoid on the bits, and I've given it a silly name in order not to tell you which one. I want you to figure out which one, so you got to give the operation that combines 2 bits, and you've got to give its neutral element, and you've got to prove it's a monoid, and then you need to prove that you really do get a preorder from that operation. So you got to show it's a preorder. And you've got to show that it's a preorder that's equivalent to implies. So hopefully the material in this lecture has been plenty. You've seen this trick done twice in this lecture, so hopefully you can do it for yourselves. And yeah, there's just a little bit of a puzzle to figure out which very familiar operation you need to pick here. Okay, I think that's probably it for this morning. Anything else to add, Fred?
Any final questions?
I'll hit stop share.
Sorry, just the wording of preorder. Does that mean that we have to prove something else before we can start doing the main questions? Is that the translation of what a preorder is?
No. Um, it, so but I guess I should, right, so to prove it to preorder is exactly to prove these two things,
Mm-hmm.
that it's reflexive and transitive. And it's called a preorder because it's on the way to being something called an order.
Uh-huh.
So so something is, so this is uh, this is, we say it's reflexive, and this is transitive. And order is something which satisfies the property that it only holds both ways round for equal things. So you know,
Mm-hmm.
for example, that good old less than or equals isn't just a preorder, it's an order. Because if x is less than or equal to y and y is less than or equal to x, that's only
Mm-hmm.
possible if x is y. So yeah, it's called a preorder because these are, yeah, partial requirements for being an order, and you still get a lot out of even just having this stuff. But that's what the pre is doing in the word preorder.
And what does an order do?
So yeah, so an order has the property that uh, uh, that there's yeah. So but
Yeah.
for an order,
You're right.
I'll not put it there. For an order, you need the property that if A is if you can get from A to B and you can get from B to A, then A and B are the same place.
Mm-hmm.
Uh,
Awesome.
uh,
Well, thank you very much, Connor.
okay, my pleasure. I should stop sharing and I should also stop the recording. I can see Fred is leaving the building. Cheers, folks.